Hello, everybody. We're going to talk about something a little bit more theoretic. It's called homomorphic encryption. The agenda for today's talk will be understanding what homomorphic encryption is. What is the origin of this idea that homomorphic encryption brings of computing on encrypted data in general? And then we'll see some toy example that I hope everybody will be comfortable with doing some additions, multiplications, modulo operations. And we will see with this how we can do some computation over encrypted data. Afterwards, we're going to describe how are we going to augment it to some really powerful notion of computing arbitrary things over encrypted data. And then we will mention very briefly some state-of-the-art schemes, techniques, and implementations if we will have time. But the general talk will be the purpose will be to deliver the higher level of this cool tool called homomorphic encryption. Okay, so what is homomorphic encryption? At the beginning, we had symmetric encryption and things were good. Later on, we got an even stronger tool that is called public encryption, public encryption. And at the same time, people, Reves, Talman, and Dertouzes asked, what can we do on encrypted data? And actually, today is April Fool's, so these are not the right guys. I'm sorry. These are the guys. So already in '78, they asked, what can we do with the encrypted data except encrypting it, giving it to somebody else, decrypting it, and that's it. So they presented this idea called homomorphic encryption. And the general description of this idea is, instead of taking my plaintext data and doing some computations on it myself, I can always use some untrusted server. But the problem is, if I give my data to an untrusted server, I'm compromising my security. So I wouldn't like to do this. What I will do, I will encrypt my data and send to the server only ciphertexts. The server will somehow, magically, we will see later on how, perform computations and perform some operations over this encrypted data. He will get the result that I asked him for. He will send it back. Now I have the secret key. I will decrypt it. I will have my plaintext result. I will have the computation of what I wanted to do without exposing my plaintext data to the server and without doing the computations myself. Cool. So let's see what is the origin of this idea and why already in '78, guys that invented the RSA encryption system started to play with this concept. So let's look at the RSA encryption scheme, a textbook RSA encryption scheme. And in this scheme, what we do, we just get the security parameter K. We generate some keys. The public key will be some number N and another number E. The secret key will be, again, two numbers. We will not dive into the details. Let's just remember that when we're encrypting something, we take some message M, some integer, for example. We raise it to the power of E, and then we do a modulo operation, modulo N. To decrypt, only the person that is holding the secret key has this magic thingy D, and he is able to raise the ciphertext to the power of D, do a modulo N operation, and receive the original message back. And what is magical already in the RSA encryption scheme, that it has the following property. If I take two ciphertexts encrypted with the same key, and I simply multiply them, do a school book multiplication between these two ciphertexts, when I will try and decrypt this multiplication, I will get the result of the multiplication of the original two messages. And this property that was already noticed back in the days is called partially homomorphic encryption. And it allows us to, let's say if we have some two groups and we have a function, and the function is some operation that we can do, we can first apply the operation, and it will be as if, and if we will first apply the function and afterwards apply the operation, we will able to interchange these two things. So, and examples of homomorphism and a homomorphic operation that we know, for example, we can take the absolute value, it's a homomorphic encryption, raising to the power of C, and lots of other stuff. And we already seen that, for example, if we take and we multiply two ciphertexts, we have encryption schemes like RSA and El-Gamal encryption scheme that enable us to receive the result of this multiplication. Similarly, we have, for example, encryption schemes. Then when we multiply the two ciphertexts, we get the result as if we added the two ciphertexts together. And this is called additively homomorphic encryption. There are another examples when you can do XOR operations. And in general, what can we do with this kind of thing? Not much. If the original operation that you wanted to do was magically the XOR operation or the only additive operation itself, then you can use these schemes. But it doesn't sound like something worth talking about. So let's do some more interesting things over encrypted data. And for this, I want to discuss the second about models of computation. The ideal thing that we are familiar with is high-level programming languages. This is how programmers and developers are used to compute over regular data. And we wish we had something that we could just write code. It will be translated to doing stuff over encrypted data, but unfortunately, we do not have something like this. So let's go a little lower. We have assembly language. We also don't have thing for this. Let's go even lower. We have things like random access machines. This is a model of computation. And we also don't have an ability to operate over these kinds of objects. Also Turing machines. And we somehow dived to the bottom where we are able to do Boolean arithmetic or even doing arithmetic or Boolean gates over just numbers or bits. And actually, all these models of computations are Turing complete. We can compute everything with them, but there are trade-offs. What we will see today in fully homomorphic encryption, in homomorphic encryption in general, we will be able to work only on these kinds of objects, the lower ones. And why are we even talking about computing over Boolean gates or arithmetic gates? As we said, it's Boolean complete, it's Turing complete. We can compute everything with this. So if I, for example, show you how to do AND and XOR between bits, we will be able to compute everything on encrypted bits. It will not necessarily be the most efficient way to evaluate some function and to do the computations, but it will be enough to compute over the things that we would like to do. Okay, so as I said, if I will be able to show you how I can do products and sums over encrypted bits, where I encrypt each bit separately, I will then can brag and go around and say that I know how to compute everything on encrypted input. And It will not be the most efficient way, but it will show you the basic concepts and ideas that are behind homomorphic encryption and computing over encrypted data using homomorphic encryption. So for example, I want to show you how can I privately retrieve data from a remote encrypted database using only additions and multiplications. So let's assume that we have some database which is encrypted of n bits, and the client holds the key for, and he is the one that holds the data. He encrypted it, sent it to some server. Now he wants to retrieve some index from this database, retrieve the value from there without telling the server what value he asked for and without revealing the server, to the server what value he actually received. So what I would like to do is that the client will learn the bit x in the point q, and the server will learn nothing. And of course, we assume that all these bits and the query itself were encrypted by the client, let's say with homomorphic encryption or with other different tools that allow computing over encrypted data. So for example, I can show you that I can compare two numbers just by running this multiplication of additions of the separate bits that represent each number. This is probably, for example, how things are done in your processor when things are done over the unsigned integers. This is how unsigned integers are compared inside the processor. And all I have to do, once I get these encrypted bits, this encrypted query, I will just run the comparison circuit over each of the indexes and the query index that I would like to receive, and multiply it by the bit in that position. All the bits that are not in position Q will be zeroed out, and only bit X in place Q will be left, and I will be able to retrieve it and get the result. And essentially what I show you, that I have this cool method of retrieving information from a remote server where I encrypt data, send encrypted query, get an encrypted result back, nothing was revealed, and all was done by computing over encrypted bits. Okay, cool. Okay, we're good with time. So I want to show you and to dive even deeper and actually present to you how I can do this over simple objects. So what objects do we know that we can add and multiply? For example, we can add and multiply polynomials. Okay, we can add and multiply matrices. But today we will see an example where we can add and multiply integers, and we will build an encryption scheme, a fully homomorphic encryption scheme for operating over integers. And through this, we will see the concepts that repeat in every homomorphic encryption schemes, even on different, more complex objects. Okay, I will have a key generation method. This method will just pick some large, random, big, odd integer, p. And this p will be my secret key. It will be a symmetric scheme, just for the simplicity. It can also be made public key. And this scheme will be, also for simplicity, it will encrypt only single bits. And we've seen if we can encrypt single bits, we can compute everything on these encrypted bits. So when I want to encrypt a bit m, I just pick a large, huge multiple of p. I pick this big integer q multiplied by p. And here I draw the numbers line where you can see, for example, lots of multiples of p. And here is this big multiple q of p. Afterwards, in the process of the encryption, I will pick some small integer, and the parity of this integer, it will be even if I want to encrypt 0, and it will be odd if I want to encrypt 1. So the parity of this number 2r plus m will depend on the message that I want to encrypt, the bit that I want to encrypt. And my ciphertext will be just the additions of these 3 elements. The large multiple of p, of my secret key, some even number, and my bit that I want to encrypt. Okay, cool. And just for the notation, we will mark this part here as the noise. We will see later on why. Cool, I have a way to encrypt stuff. Now, when I get a ciphertext, it will be some large, huge integer C. I would like to recover my original bit that I encrypted. So what I will do, I will do something that is called centered modulo. It's actually doing a modulo operation, afterwards centering the result to be between p minus p divided by 2 and minus p divided by 2. So just centering the modulo result. And when I center the do the centered modulo operation, I am left essentially with this value 2r plus m, because the number p, as I see here, was a multiple of q, so I just get rid of it. I'm left with this thing when I decrypt. And afterwards, I just do a modulo 2 operation to get rid of this value 2r. And I'm left with the original bit that I wanted to encrypt and later decrypt. Okay, cool. So I hope it's not too mind-blowing. We're just doing additions, multiplications, and modulo operations here. And let's discuss about the security of the scheme. So how secure is it? Well, if I will have this noise value equals 0 every time, and for example, I get 2 encryptions of 0. So I have this first encryption of 0. I don't know how to, oh, here. I have this first encryption of 0 and another encryption of 0. And my secret key is p. And if the noise was equal to 0, it will be very easy to retrieve the value p. I just do a greatest common divisor operation and get the secret key, and this is how I break the whole scheme. But this will not work when I have noise, when I have this 2r value there that I add to the while encrypting. And actually, we believe that any other attack doesn't exist when you choose the right parameters, do everything correctly. And this assumption, this hardness assumption, this security assumption is called the approximate GCD assumption. Cool, so I have a way to encrypt, I have a way to decrypt, it's secure. Now, let's see how I can do operation on these bits while they're still encrypted. So if I will show you how to do XOR, and I will show you how to do an AND, it will be Turing complete, and everybody will be happy. We will be able to compute everything over encrypted data. Again, this is just to show the concepts. It's not efficient. It's not the state of the art of what we do when we operate over encrypted data, but it's just to show you the concept itself. So I have 2 ciphertexts here, C1 and C2, that are encrypted with the same key. If I just add them and change the places of the objects, of the elements, I can see that I still have this multiple of p here, still have the multiple of 2 there. And when I do this centered modulo operation, I'm left with this value over here. When I do a modulo 2 operation, I'm actually left with this thing here after modulo 2, and we have a dog here. And this is exactly the XOR of the 2 messages, 2 bits. Bark if you understand. Okay. And if I want to do an AND operation, it's very simple. I just multiply the two values, and I get, again, reordering of the elements. I get something times p, something times 2, and the multiplication of my original 2 bits. Cool. I will do a modulo p. I will do a modulo 2. I will be left with the multiplication of the two values, and everybody will be happy. But the things are more complex. And let's discuss about the noise. This thing here, we called it noise. And we will see that, okay, when we add two ciphertexts together, we have the noise multiplied approximately by 2. The noise grows a bit, but not too much. But when I multiply two numbers, two encrypted numbers, two encrypted bits, this noise doubles, squares, sorry. And what does this mean? Well, it means that we have now noisy stuff, and it will cause us a headache. Why it will cause us a headache? For example, let's say my original message was encrypted, and the encrypted value landed somewhere over here, and the initial noise was small enough, and we were able to decrypt, and everything was fine. But let's say that after enough multiplications and enough additions, and less additions than multiplications, the noise grew much with each operation. And if this value, the original noise modulo 2, the original noise plus the message modulo 2, is different from the new noise, we're actually decrypting and we're receiving the wrong bit. So we have an error, and we're in problem. We have problems. So this can happen when the noise grows, for example, in this toy example, or bigger than the minus p divided by 2, or sorry, smaller than minus p divided by 2, or bigger than p divided by 2. Okay, so what have we accomplished so far? We've seen that we can do lots of additions because we've seen that addition does not add too much noise. We can do some multiplications, but the noise grows, and after a little bit of multiplications, a little too much multiplications, we will not be able to decrypt correctly. And what we actually constructed now is something called somewhat homomorphic encryption scheme. What does this mean? We can do some multiplication, some addition, so we can solve some problems, and we can compute some low depth circuits over our encrypted data. And this is already enough for some useful applications. For example, as we see in peer, private information retrieval over some small database of bits, of maybe a couple of bits, nothing too fancy. And actually, any kind of algorithm that we can implement it, model it as a polynomial with some logarithmic degree. The degree of the polynomial of our algorithm will be only logarithmic. And not many algorithms and not many computations fall under this definition. So we're here to do some more complex computations. So we will show you how we can do much better than what we have achieved so far. And for this, we'll discuss how we can compute arbitrary functions without any limitations over encrypted data. And okay, so what we've seen so far is a somewhat homomorphic encryption scheme, and we are still unable to compute some arbitrary circuits or arbitrary functions over our encrypted data. And as we've seen, since it was suggested, this idea of homomorphic encryption in '78, this was the state of the art. We weren't able to compute many interesting things over encrypted data, but it changed. It changed in October 2008 when this guy, Craig Gentry, came up with very cool idea how we can augment encryption schemes, homomorphic encryption schemes, to compute arbitrary functions without any kind of limitations. So let's see let's see the idea itself of how it is done. So we've seen when we compute, when we encrypt, we add some little bit of noise to the ciphertext, and the noise grows a little bit. And when we go over this limit here, we're no longer able to compute on these ciphertexts. And the problem is sums and products increase the noise until everything blew up. So the solution for this problem will be some noise reduction mechanism, and this was the main bottleneck and main problem that was open for 30 years. Nobody could find a solution for this, how to reduce the noise. But let's think about it for a second. What can be the best noise reduction procedure? Why not decryption? When we decrypt something, we are just left with the plain text value. So essentially, we just remove all the noise altogether. But the problem is, okay, if I want somebody else to do decryption for me, I need to send them my secret key. And this will expose my data and will expose everything. But why not encrypt the secret key itself and give to the server the encryption of the secret key? And now what the server will do, he will evaluate. The decryption function itself is also a circuit, some kind of circuit. So if I give the encryption of my secret key and my encrypted bit to the server, he will now be able to evaluate the decryption function on ciphertext, and what he will output is the bit itself still encrypted, and as long as the noise in the bit here is larger than the noise in the bit here, we're able to decrease the noise, and this way we will be able to continue computing more and more over the encrypted data. So this is exactly what it says. Regardless of the noise in the input bit here, the encryption here, we can always encrypt the secret key and use fresh encryption of the secret key. So here the noise will not grow. And when we will run the decryption algorithm with the decryption circuit over the bit here and the secret key here, we will be left with a new encrypted bit, but with less noise. And this is how it's depicted. We are draining some of the noise from this ciphertext, yes. Because we evaluate this thing homomorphically. When we evaluate something homomorphically, it's as if we're computing over encrypted data, and this thing is still encrypted. Mind-blowing. This idea is kind of mind-blowing, but this was the explosion in the field that started a series of genius works that we'll discuss later on. And for example, if I do more computations here, I can always run this bootstrapping operation again and again, and I am able to continue computing. So if we will think about the world of things that we can evaluate, things that we can compute, has this yellow thingy here, and the blue thing here will be the whole world of computable. If I have this decryption, the homomorphic decryption mechanism here, and afterwards some AND or multiplication of these two ciphertexts here, this is some kind of circuit. It is located here somewhere in the universe of circuits. And also, I will have the same thing with XOL. It's located over here. And if I will build an encryption scheme that will be able to compute this thing here and this thing here, I will automatically get the ability to evaluate any function over encrypted data. And okay, this was the mind-blowing idea that came in 2008. And now, so let's discuss briefly about what happened in the last 10 years. State-of-the-art implementation, schemes, and so forth. So we've seen hardness assumptions, but actually computing over integers is not very efficient. And this hardness assumption of approximate GCD is cool. But nowadays, what we have is actually a mathematical object called lattices. And most of the homomorphic encryption scheme work over lattices. And for example, we have, I've put, the presentations will be shared later on. So these are links to the actual papers. And there are lots of hardness assumptions related to lattices, for example, learning with errors, ring learning with errors, entro, and they are much more efficient than just working over integers. We have, since then, lots of optimizations and better noise management techniques. So, for example, we've seen bootstrapping, and the thing is, bootstrapping seems magical and wonderful, but it's actually very, very slow because the decryption circuit is most of the times complex. So it takes about a couple of minutes to evaluate the decryption circuit over each ciphertext. It's not very realistic and it's very slow. So later on, different approaches were invented to manage noise. For example, we can think about an encryption scheme where after each multiplications, we perform multiplications, and we know that multiplications are very heavy. So we just do some more magical mathematical stuff that just clear away the noise. And when I build this kind of scheme, I just need to tell, while initializing it, how many levels of multiplication that I would like to do. It will initialize it appropriately, and I will be able to compute any circuits to a certain depth, to a certain multiplicative depth. We have something very cool that is called ciphertext packing. And if you're familiar with hardware, it's as if you're doing a single instruction, multiple data operations, SIMD operations over one ciphertext. You have one ciphertext. Inside one ciphertext, you have lots of values stored inside. And when I add two ciphertexts, I add all these values together. When I multiply the ciphertext, I multiply all these values all together. We have even better and different mechanisms to clear away the noise and deal with the blow-up that we have after each multiplication. It's called relinearization. We have cool stuff called key switching and model switching. And you can think of that, well, you can, similarly to this idea of leveled encryption, leveled fully homomorphic encryption, you just use a series of different keys that you change key after each multiplication. And this is how you keep on rolling and doing more and more operation on each ciphertext. We have something called scale invariance, where the noise, I always forget this, so from here, where the noise itself is dependent only the rate between some parameters and does not grow and blow up as you do the computations. And a recent invention from 2 years ago is something called rescaling that enables you even to compute over a floating point or fixed point numbers and do computations not over integers, not over whole numbers, but over fixed point or floating point numbers. And the state-of-the-art schemes that I consider today are the scheme over the integers that we saw. People use it for mainly for toy examples, but it still exists. We have this encryption scheme, BGV, that is based on one of the hardness assumptions that I mentioned, ring learning with errors. It has a very efficient noise management, and it's also leveled. We have BFV, which is same as the previous one, but it's scale invariant. We have GSW, which is a different idea on how we can compute and do noise management, and it's actually considered conceptually simpler. We have LTV scheme, which is based on untrue. We have the scheme over floating point numbers that I mentioned that allows approximate arithmetics. And all these are the links to the papers that discussed these schemes. And we have some open source implementations, state-of-the-art implementations. We have the most old library, but it considered the most efficient one, and the most advanced one is Hilib, and it is based on BGV. It is written in C++. It is maintained as an open source by IBM, and it has various optimizations. It's considered the state-of-the-art scheme. We have Seal by Microsoft, which is very similar to this one, but it is based on the BFV, and it is well documented. And if somebody is considering to diving into fully homomorphic encryption, this is the way. This is the place to start. We have Palisade that does general lattice cryptography. We have FHEW that is very cool because it has fast bootstrapping. The bootstrapping there is very fast, but this is while keeping the scheme itself very, very simple. So it's not very, as you call it, production ready. We have another scheme that is based on, these two are based on the GSW construction. We have this thingy that allows us fixed point arithmetics. And another thing, the only thing, as you can see, everything is written in C and C++, and this is written in CUDA. This is the only one, and it allows you accelerate. It allows you to run it on CUDA devices. I have some additional links here, and to summarize, what we've seen is we can compute arbitrary functions on encrypted data with fully homomorphic encryption. It's very cool. And there are many schemes, there are many implementations. Further details we haven't seen, we haven't discussed performance, and as I mentioned, it's quite slow. And if you choose fully homomorphic encryption as your solution, you need to be aware that it's very slow, and you need to adapt accordingly. There are other limitations. For example, how do you support multiple users? And there is a whole research area on how you implement algorithms and how you implement efficient tasks using full homomorphic encryption, and how you build your whole scheme using full homomorphic encryption. And that's it. Thank you.
Question?
Great talk. A couple of questions. First of all, you said that you can basically compile, pretty much run any functionality. What happens if you have a functionality that, you have like a loop with a secret, like a while loop, and the condition is secret? How do you compile that down into a circuit?
As I said, you are able to compile everything to circuits. And in circuits, more problematic. It's more problematic to do loop kind of behavior. But you can always imagine that you can put some upper bound on your loop, and you always do the loop until the end, and you have some kind of encrypted flag that is raised if your condition is met. You actually stroke the one of the problematic implementation. One of the difficulties in implementing real algorithms and real high-level programming languages using fully homomorphic encryption, because you don't have all these higher-level mechanisms, and you have to adapt and convert it to circuits. And when you convert it to circuits, you're stuck with this drawback that you cannot have a circuit with a big multiplicative depth, because it will be ultra slow. So you will have to think how you can parallelize it, or how you can adapt it, maybe lose precision, and then achieve lower circuit depths. This way you will be able to do it faster. For example, one of the things that we've done, searching over encrypted data. We've shown how to search over encrypted data using fully homomorphic encryption scheme, and we made it faster by losing precision and using an approximated scheme, but it allowed us to build a circuit with very, very low multiplicative depth, and we achieved, for example, results that you can compute searches instead of days, 2 hours. So this is the general example.
Thanks. One more question is, you talked a lot about secrecy. What about integrity with FHE?
Here, okay, this is another topic. In all our constructions, when you use only full homomorphic encryption scheme, you assume that your server and the one that is computing over encrypted data is what we call honest but curious. What he does, he follows exactly your instructions, but he tries to sniff around your data. If you want to add integrity, and if you are considering malicious servers, you need to put different cryptographic tools. For example, verifiable computation. This is a different cryptographic tool that allows you to receive some kind of verification that, okay, this computation was done and nothing was compromised. Nobody have done something else that you didn't ask them for. But if you combined verifiable computation and fully homomorphic encryption, you will need to ask your grandchildren for the result.
So, can you explain us why exactly is homomorphic encryption considered to be quantum computers resistant?
The thing is, the homomorphic encryption itself is not quantum computer safe. You cannot say on homomorphic encryption that it is quantum computing safe, but you can say on some specific scheme that it is quantum computer safe. For example, you know that RSA is not quantum computer safe because there are algorithms that know how to attack RSA. But we've seen that most of the fully homomorphic encryption schemes are based on lattices. And all the lattice problems, we don't know how to attack them, even with quantum computing considering in mind. So this is why sometimes people say that fully homomorphic encryption is quantum computing safe, because it is state-of-the-art schemes are based on lattices, and all the hardness assumption in lattices, we do not know quantum computing algorithms to attack them.
I think that was the last question. Anyone? Okay, great. Thank you very much. Thank you very much, Max, for the talk. Just before we leave, I just want to thank Enigma and Max for coming and explaining their work. Also want to thank Microsoft for allowing us to use this amazing space and all the setup they have with it. And also, because I always forget to do it, I want to thank Omer, who's organizing with me this event and who's making always a great work with everything. So if you can even give me a round of applause, it would be amazing. Just two things coming. First of all, we are always looking for speakers and continuous sponsors if people were interested. Please come to us and suggest ideas or suggestions about like whatever. I would be very interested. We are also going to start event in London, which makes it, and the first one should be with Dara Upwood from Zcash, if anyone knows about her. She's amazing. And the second one is going to be announced later, probably later this month. And if you want to have access to the content, I invite you to either subscribe to the YouTube channel or to go on the Facebook group or ask ourselves, Omer and I, directly if you want to have access to the content, if you're really not on Facebook. Thank you very much, everyone. And there is still drinks and we can keep talking. Have a great day.